We're going to now define a dimensionless group that tells us how effective the fin is relative to the situation in which we have no fin at all. We define a dimensionless group for fin effectiveness. This is epsilon sub f, which is defined as heat transfer through the fin, given by Q sub f, divided by heat transfer in the absence of the fin, given by Q sub a. We'll define Q sub a first. Q sub a is how much heat is dissipated when we remove the fin through whatever area is left over on the base. This is the area that the fin was previously covering up. That area is defined as A sub c. It's just the cross-sectional area of the fin. If we take that and we multiply it times h, the heat transfer coefficient, and the excess temperature at the base, theta sub b, we know how much heat current is being transferred in the absence of the fin. This is Q sub a. We can now determine how much heat current is transferred through the fin. And one way of doing this is just by considering whatever heat comes in through the base of the fin. Whatever comes in through the base of the fin is ultimately what is dissipated from all the surfaces of the fin. So the heat current through the fin is Q sub f equals minus k times A sub c times dt dx at x equals 0. This is taking the heat flux at the base of the fin, multiplying it times the cross-sectional area, and that gives us a heat current for whatever heat is going into the fin, which is ultimately what the fin dissipates. We can plug in for T with the excess temperature theta, obtaining this. Now we can make use of our solution for theta, and we obtain this as our final answer. That we have the square root of h times p times a sub c times k, all of that times theta sub b times the hyperbolic tangent of m times l. We can take now these two expressions for Q sub f and Q sub a, take their ratio, and we now have an expression for the fin effectiveness that it equals the square root of k times p divided by h times a sub c times the hyperbolic tangent of ml. The hyperbolic tangent of ml is a function which saturates at 1 for very long fins or for large values of m. This means that the maximum heat transfer through the fin is given by simply setting the hyperbolic tangent equal to 1. So Q sub f max equals the square root of h times p times a sub c times k, all of that times theta sub b. We can now plot Q sub f divided by Q sub f max. We can plot this as a function of m times l. We know that Q sub f saturates for a large m times l at a value of Q sub f max, which is shown here in this plot. This means that there are values beyond which it is useless to continue to increase m or make the fin even longer. Q sub f divided by Q sub f max reaches a value of 99% when m times l equals 2.65. So for fins which have a dimensionless length, that given by m times l of 2.65, lengths beyond this don't really offer very much. We're going to go from 99% of the maximum heat transfer to a value that goes just beyond this. So this is a good rule of thumb to remember when it comes to sizing a fin. Of course, one could have a different constraint depending on the specific situation.